done the following thing. We essentially proved the Seledit's theorem in a deterministic setting for the dimension 2. Well, by which I mean for 2 by 2 matrices. A of n by definition is an a1.
Well, we proved it under the assumption that the limit of the larger exponent is positive, right? That was the main assumption that you made.
That's exactly true. I will say it again. So this is presented in the form. It is just a convenient thing. I actually didn't use much of it, but it is useful to remember that this is d1 of n, d2 of n, 0, 0, vn. And what we essentially proved is the following thing. Suppose that if 1 over n log of d1 of n converges to what I called gamma, I hope.
Gamma, yeah.
Good, thanks. Which is strictly positive, and also if the norm of an log of the norm of n divided by n converges to 0 as n tends to infinity, then there is x0, norm of x0 is equal to 1, such that 1 over n log of the norm a of n x0 converges to minus gamma, and for every other x 1 over n log of the norm a of n x converges to gamma as n tends to infinity. If x is not equal to x0, is not proportional to x0. So how should I say it? Is not c x0.
Is not.
Not. Thanks. This is what we proved. Well, this theorem, in fact, was used. I mean, there are two hypotheses here, essentially. First of all, that the limit exists. The very fact that the limit exists is not all simply not, generally, this is simply not true. You cannot say that if you have a sequence of matrices, bounded or whatever, you will always have the limit there. Of course, this is a strange thing to believe a priori. And the second thing is, why should this limit, even if it exists, be positive? And of course, if you have these two properties, then everything follows, but why do you have them? And this is what, well, so there are two questions. Why is it reasonable to consider or to have the hypothesis that the limit exists and 2 why and or under what conditions at least under what conditions gamma is larger than 0. So I will first answer the first of these questions and then the second one, and I hope that I will be able to explain the proof of the Furstenberg theorem which answers the second question. There are many answers to it in a sense, because there are many theorems claiming that this limit is positive for different classes of matrices. And I will, but the answer to the first question is given by the subadditive ergodic theorem. So from now on,
You said it's the Furstenberg theorem. Maybe you want to write it. Not everybody in the audience will know.
the name or the theorem. The theorem will come up later, of course. And the name too.
But you mentioned the name. The audience doesn't know what to do with the name that you don't write on the board. They're just confused.
Yeah, thanks a lot. You know, it's a very useful
Anytime you say
statement,
name,
actually,
you have to write it on the blackboard.
because when you are involved in this business, you cannot imagine that somebody can be unaware of this name. But Furstenberg, Philo, an outstanding mathematician, I can assure you. Absolutely outstanding.
I think we should put Kingman's name on there too, no?
Sorry?
Kingman, for the subadditive.
I haven't yet come to Kingman, but he was mentioned a number of times here, and his subadditive ergodic theorem was explained already by Leonid, so I don't have to write his name probably, but I will.
In fact, the first proof was not, they do not use, they didn't use.
So,
The proof that norm converges, it was Furstenberg and Wells
and Kesten,
and Kesten without subadditive.
yes.
To simplify it strongly.
I will just now discuss it. Then, sorry. So from now on, an is a of t to the power n, actually n minus 1 omega, where omega f p is the probability space, t is a measure preserving transformation, measure preserving transformation of omega, and this of course is preserving the measure p. This is what is called a dynamical system sometimes. It's a dynamical system in quite an abstract sense. There are many concrete dynamical systems.
You don't need ergodics?
I will suppose that it will be ergodic, yes. So T, but it is not really essential, is ergodic. Simply in order to avoid these things. Let us note that then A of n, then A of n will be, of course, a random matrix. So we have a function A, first of all, A of omega. Let me simply make sure that A is a function, right? It maps omega into SL MR. Right now, it will not be important what M is. It is not 2. It is arbitrary. We shall see that it can be even infinity, even equal to infinity. And this is the absolutely remarkable difference between Kingman's subadditive ergodic theorem, which works for this case, and the theorem which was proved, as Leonid mentioned it, by Furstenberg and Kesten in 1960, before Kingman had a chance to say a word about the subadditivity in this thing. So A of n omega is this product now. A of t to the power n minus 1 omega, A of t to the power n minus 2 omega, this is a n minus 2, A of t omega, this is actually A of omega is 1. This is this will be A2 if I put, okay, so it stops at A of omega. And it has the following properties, this thing, that the norm of A of n, say, plus k omega will, of course, be less than or equal, and I will use the property of the norm, which says that the norm of a product of two matrices, or operators if you wish, is always less than or equal than the product of these operators. That's the product of the norms, just of two of them. Namely, I will write A. I will not write all of that like this. It will be, this is AN, this is A1. So I will simply skip this long notation, but everybody should understand that I am now dealing with matrices of this form. So it will be A n plus k. I will write here A n plus 1. Then there is A n, so A1. And this will be less than or equal than the norm of A n plus k A n plus 1 times the norm of A n A1. I'll put it this way, log of the norm of A of n plus k omega will of course will be less than or equal than the sum of logs, log of the norm. But what is this? This is A of k. T to the power n omega. This is the log of that. And this is log of the norm of A of n plus. And what do we see here? We see that there is a subadditivity property which is required by the subadditive ergodic theorem in order to apply it. So, in these three lines, if I know the subadditive ergodic theorem, I have proved that with probability 1, hence, with probability 1, there is a limit 1 over n log of the norm A of n omega, which is a constant because we are in the ergodic situation by definition. But it can be actually it can be a random number and still exists with probability 1. The only difference then will be that this gamma will depend on it. So in general, it is like that. What I have not said here is that what we need is that the log, that the expectation of the log of the norm of A of omega is finite. Let's put it this way.
So
Now,
we should feel it's reasonable to have the hypothesis because there is some powerful theorem in the background that ensures.
no,
So what's the logic here? I'm not getting.
good.
You're not yet in the process of proving anything. You still.
No. I proved. I proved something. I proved that for stationary sequence of matrices, whenever you multiply them, you have the limit. This is a statement I have just proved. This limit exists if your sequence of matrices here is not just a sequence, but is picked up from a dynamical system and is a stationary sequence of matrices. In particular, if we have these matrices, let us always have in mind this example, Aj is equal to Qj minus energy minus 1, 1, 0, and Qj is simply a stationary potential in our beloved, simplest Anderson model, one-dimensional. We know that the Lyapunov exponent exists. We don't know yet whether it is positive or not. But the existence is there. And all what you need is a stationary potential. Not independent, nothing else. So it's a very powerful theorem. And here I am saying that Kingman's theorem is a very powerful tool. Which was
just to make a connection, I use the term homogeneous, not stationary. just mention it because others
Okay. Measure preserving transformation explains everything. I have nothing against homogeneous or stationary. So both terms are equally good for the description of this situation. There are many examples. In particular, if QJs are independent identically distributed, of course we are in this case, in this situation. We have this limit. It exists always. There is no question about the existence. This was a problem. In 1960, when the whole thing started, if I'm not wrong, then it's Bellman who initiated the study of products of random matrices, and who actually asked the question, and I think he did something about it even. And so Furstenberg and Kesten, they were prompted by Bellman to look at this question, and they proved, using a completely different method, that for finite dimensional matrices, you really always have this limit. Formally speaking, their paper refers to products of positive matrices, because they wanted not just the existence of the limit, they also proved some central limit theorem for them and some additional hypotheses. But this is essentially, they did it and nobody has ever disputed it, because the proof doesn't depend. The proof of this part doesn't depend on whether or not the matrices has positive elements.
Positive means with positive elements.
Yeah, positive means in this context positive elements. Now,
Question.
yes.
How do we know that gamma does not depend on omega?
This is because this is a part of the statement of ergodic theorem. If T is ergodic, then gamma doesn't depend on omega. T is ergodic by definition.
Yeah, okay.
Yeah. So this is what is happening now. Why I'm saying that is that I mentioned already that M may be even infinite. It doesn't make much sense when I say that M may be infinite when I am talking about the group SLMR. It is not a very, it's not a very meaningful statement, because there is no SL infinity of, or you will have a hard time to define it at least. But what I mean is that I don't use here anything concerned with the structure of matrices. I use the fact that matrices are operators. It is a particular case. So if I have a sequence of operators which have a norm bounded still, something has to be there, and such that this thing is integrable, then everything is fine, the limit exists. And this is absolutely impossible to do. I mean, to prove a thing like that is impossible by methods used before Kingman's subadditive ergodic theory was invented. So it's an actual breakthrough there. In this respect, at least, well, this theorem, this subadditive theorem, has so many applications that this is just one of them. But to me, it is one of the most convincing facts and most important implications, of course. Namely, to the case when the matrices are infinite dimensional. Now, this in fact was used later by Ruel when he considered products of infinite dimensional operators, and in dynamical systems it played a very important role, and in the study of many things. Okay, now what we have to discuss now is also why is this coefficient strictly positive, or under what conditions it will be strictly positive. Now this is another theorem by Furstenberg, but of course you need certain restrictions. It is very easy to construct an example of matrices which are perfectly random, stationary, but not, well, but and the limit of course exists, but it will be a 0 here. And in this case it is not very interesting because we cannot say anything about it, and because the behavior is not defined by the dichotomy of the space. Okay, so I'll now state a theorem which belongs to Furstenberg, and I will try to explain at least the ideas which lie behind the proof of this theorem, and I even hope that I can actually explain the proof. I'll look at it in a more general context than just the 2 by 2 matrices, because again it's more natural actually to look at it in this context. So Furstenberg. Yeah, well, it's not a very good thing to say the Furstenberg theorems, but it's really one of the most well known of his results. But he has very deep and very nice results also in other areas, which have very little to do with this theorem. So he has many theorems, and they are all non-trivial. So what I will be talking about is the following thing. I need some hypothesis first. Let Aj be a sequence of IID matrices. Matrices with determinant 1. So they are not just random, but they are also identically distributed and independent. Well, like this. Those who prefer not to think about very abstract matrices, they can think about this particular case, which is very, very instructive. And then independent identically distributed matrices means simply that Qj is a sequence of identically distributed and independent random variables. I will introduce the measure mu on SLMR. Mu of gamma, by definition, is the probability that A omega belongs to gamma. Gamma is a subset in SLMR and the set of matrices. I'll call G mu the group generated by the support of mu. Actually, I will always consider the closure of the group. S-U-R, sorry, closure. Oh. Group generated. Of course, it is a group. Sorry? Yeah.
So he has a set inside SLMR, and he takes, and there's a set inside a group. So all the elements of this set are group elements, the bigger group.
No.
And I assume that he now takes elements from this set and multiplies them together. And then he
Yeah.
closes it up,
That's correct.
and that will give a group.
Yeah. I think that the actual question that one has to clarify here, what is the support of a measure? It's a very useful thing to remember. So it's a definition which, even though is a very simple one and well known, I will repeat it. So what is the support of mu? Support of mu is the set of matrices A in SLMR. It doesn't have to do much with matrices. It can be anything, any metric space, such that U epsilon of A is the probability or the measure of U epsilon of A is strictly positive, where U epsilon of A is an epsilon neighborhood of A. So if I take a set, if I take a point A, I consider a small neighborhood on the group, of course, of A, and whatever the radius of this neighborhood, the measure of this ball will be strictly positive. This is what is called support. Support is always a closed set. Yes?
Maybe you should write for any epsilon.
Yeah, I said for any epsilon.
But you must write it. We're not so fast.
No.
Right.
I only say that I didn't miss it, but I don't object right. Don't have to justify. That's absolutely correct. No, one has to write. So this is what a support is. So it's always a closed set, and you take all the matrices from the support. What is G mu? You simply take all matrices, multiply them, G1, Gk, to different two powers plus and minus 1. Let me plus minus 1. This will be a group, of course. All these products, they will form a group already. If you take the closure, it will again be a group. So all these products, they form a group.
Well, let's see. If the support of mu does not include the identity,
Yeah, but I have plus minus 1, so G multiplied by G to the power minus 1.
definition that
It is generated, it is by definition the group. But of course, as I said, what in fact you have to consider are all these words. It's not a very constructive notion. One has to say that this is a pretty strange thing. You can, of course, write that you can say that you are looking at all products of all possible matrices from the support, but even if you have two of them in the support, which is a very typical situation and very interesting one already there, to imagine what sort of a group you will actually end up with is not a simple thing to do. and it may be a very complicated group at the end.
But we should imagine the support is somewhere here, the closed group,
Yes,
and then I can apply the inverse operation of the group,
yes,
produce another patch.
exactly.
So we're working with both of them.
Yeah,
When
we
multiply
are working with
particular
both of
negative-
them. As I said, I have plus minus 1 here. So in any order, I take them, and this is the support.
And then by closing this up, you get a group.
It is a group, but it may not be closed, but you also close it up. This is not a...
You want to work with the closure.
Yeah. I mean, already this... Well, I should then write a closure here. This line means a closure. But already this thing is a group. This is a group. All these products, they form a group. If you multiply 2 of such elements, you get again an element of this size, of this form. And the inverse is there. There is no problem with that. Now, even though it seems to be not very constructive, we shall see in a couple of minutes that, in fact, you can very well use what Fürstenberg proved. But I have to state it first. So this is G mu. We need another definition. A measure kappa on a unit sphere is reserved by a group G. In my particular case, I'm only interested in G mu. If G kappa is equal to kappa. What is a measure on a unit sphere, and what does this identity mean? Of course, what I mean is the following: that G acts on a unit sphere. It sends a unit sphere S into itself by the following action. Gx is mapped into Gx divided by the norm of Gx. And G kappa of any gamma, now gamma is from a sphere, is the same as kappa of G to the power minus 1 of gamma. This is the definition of a measure preserving action on a sphere.
Well, first of all, why is this a mapping from the sphere to the sphere? So x is a unit
If x is a unit vector, I take Gx, apply a matrix to x divided by the norm of Gx. It is again a unit vector.
Gx down there. The denominator should be Gx.
Thanks. Oh, I see how I confused it. Okay. How I managed to confuse it. But thanks, yes, sure. I'm sorry. So, of course, it is not a unit vector in general. And then this is the definition. Well, Fürstenberg's theorem, which I can now state, can be stated in a number of ways, but the one which is very useful to us at the moment, I hope that we shall have the time to look at some other versions, is the following one. So this is the theory. Suppose that no kappa is preserved by G mu, then gamma is strictly positive. Yes?
If you take some trivial measure, say 0,
No. The measure, by definition, will always be probability measure. Forget everything other than probability measure. Okay? So this is the statement. No, I don't know whether
so kappa is a measure on the unit sphere,
on a unit
and
sphere.
I believe in Rn.
Yes, only I always look now deal with the only space Rm. Matrices are m by m as before, and the sphere is m-1 dimensional. And there is a probability measure, any probability measure.
So I can take the Fabini-Studi measure, so the uniform measure on the sphere.
You can. It should not be preserved by the whole group. G mu. It should not be preserved, right? Then, as every other measure. Okay. I don't know how it sounds to you, to those who, in my view, those who never looked at how to apply this theorem cannot be convinced that this is something constructive. That's my view. But if you already are convinced, the better it is. Nevertheless,
Seems like you will have to check many cases because you have to show that no infinitely many.
yeah,
Then,
yes,
understand.
it doesn't sound terribly constructive. Of course, you have to understand what is happening with every measure on a sphere. Hell knows how many measures are there, and how can you expect to deal with in a lifetime? Now let's see whether we can do it in our concrete example. And then I hope that it will be clear that it is really a constructive thing. Now I need a calculation here, a very elementary one. So I will not hesitate to take it from this sheet of paper. So our matrices are in principle of this form. A is Q minus 1, 1, 0. I want at least two matrices in the support from the initial distribution, which simply means, in simple words, that the random variable qj there, will take at least two values. I claim that if I have these two different values there, at this point, at this place, then the group generated, this group G mu, will never preserve any measure on a sphere. And a unit sphere, in my case, is simply a circle, right? So I have this circle there. This is x1, this is x2, there is a unit circle, and there is a measure, which is a very abstract object because there are still too many measures there. Even probability measures, let alone anything else. So how do I check now that no measure is preserved by g mu. I do the following thing. I simply look at a. First of all, what is a to the power minus 1? I would like to know what is a to the power minus 1. This will be this matrix. It is 0 here, 1 minus 1, q here. Right? Right. You can easily check that I didn't make any mistake simply by multiplying these two matrices. I now want to do another calculation I want to consider. And here I will have to multiply two matrices with different q's. So I will take aq times a q tilde, say, to the power minus 1. And you can again easily check that this will be the following thing. It will be 1, 0, 1, and now I usually q minus q tilde. And it is absolutely essential that this thing is not 0. Of course, I can also multiply aq tilde from the left on a. And this I will also want to do. aq. And this is equal to 1, 1. There will be 0 here. And here I think it will be the same number just with a different sign. So it will be q tilde minus q. Let me call, for brevity, for the purposes of brevity, this thing by, I will denote it by a. A is q minus q tilde by definition. And let me see what happens. What do I call this? Okay. I will call this G. Again, in order not to write all the time G, this matrix. And one last and very elementary calculation tells me the following thing. The G to the power n is any integer, actually positive or negative, doesn't matter. You can easily check it. It will be 1, 1, 0, and a. This group, you see, this thing is actually itself a subgroup of the group of matrices. All these g to the power n, all these powers, simply them alone, they form a subgroup in the set of matrices. Let me now see what happens when I consider the following sequence of vectors. G to the power n, I would like to apply to the vector x1, x2, any vector x1, x2, and I will divide it by the norm. This is my action on the space of vectors of this thing, g to the power n x. X is x1, x2. It is any vector but a unit one. So both components cannot be 0 at the same time. Oh, it's a very simple thing. I will have here, well, what will be the first component of this vector? I simply apply this matrix to the vector 1. It will be x1 plus na x2. And the second component is even simpler. It will be simply x2. And what will I have here? I will have the norm of this vector. So it will be a square root of x1 plus n a squared plus x2 squared. So
X2 is missing from the parentheses.
x2, exactly. Now let us check what happens as n tends to infinity. What is the limit of this vector? If x2 is not a 0, then this will grow linearly, the whole thing, actually exactly like na by absolute value of na times x2. And this will be negligent, and this will converge to plus minus 1, depending on the sign of this guy, plus minus 1. And here we will have a 0. But if x2 is a 0, then we immediately have plus minus 1 here. This means the following thing. The meaning of that is very simple. That once you see, strictly speaking, I only need a half of a sphere. I don't need both parts. Plus minus is there. This is a redundancy, as one says here. But in principle, this means the following, that every vector is attracted to a vector whose first component, this one, is 1, to this vector. I already mentioned to you that I usually identify these two points. They are the same point, because I am interested, in fact, in lines, not in vectors. But this is just a more convenient language. So they all converge to here, which means the following, that if you have a set there, any set there, it will gradually be here, or in any small neighborhood of this vector. Wherever you start, after a certain number of times, you will be there. Which means the following, that the only measure which can be preserved by this group alone, is a very simple measure. It is a measure concentrated on this point. But I also have this guy here. And you, of course, can already guess that this one will preserve the only measure which is concentrated at this point of the sphere. So there is no way in which the group can preserve both measures. Now, I explained all of that, but there is a very good lesson to learn there. You see, if you have in this group G mu, let's go back to G mu. So, in particular, I proved that the Lyapunov exponent Leonid was discussing in length here is strictly positive, right? In a very general situation, all what I need is that in the support of this potential Q, there are two values. Now I want to go back to this definition of G mu, which seems to be not very constructive. All what you need to find a matrix which attracts everything to one point, and then you have to find another matrix which attracts everything to a different point. And then you never have a measure which is preserved by G mu. So if there is a power of a matrix which has this property, I mean, there is a matrix such that its power has this property, then you are done. Now, there are many similar tricks which you can do with matrices, but they are of the same order of difficulty. So they are not difficult, with the only exception that it may be very difficult to find a matrix like that. In our particular case, you will have to make huge calculations, not like in this particular case, in order to find these matrices. Yes?
You mentioned here that if x2 is negative, it should go to -1.
Yeah, I said it can be plus or minus 1.
Certainly, if I put the x2 negative
What is
If you
confusing?
get x1 positive but x2 negative for your initial vector, then it should pass that stable point. So it should go out the same circle in the lower space.
If x2 is positive, right?
x2 is negative and x1 is positive.
x1 is positive. Then what?
No, x1 is positive, x2 is negative. So it's in the second quadrant.
x1 x1 is positive and x2 is negative. Then
Then
it will.
go that way.
Um,
It should pass that.
did I? Sorry. Now x2 is here, right? I looked at the wrong.
Okay. Okay.
Yeah. Okay. Fine. Good. There is no confusion anymore. Cannot be confusion. I don't see how you can be confused with this thing because there is a clear limit there. Whatever confuses you in this particular case is obvious. Anyway, let me go back.
So now in this case we see why it's reasonable to suppose, or under what condition we may suppose that there is no kappa which is preserved by G mu. But now you need to prove the theorem first.
Yes. Well, you are sometimes more generous to other lecturers. They didn't prove a lot of theorems here, but I promise to.
Give the idea.
Yeah, I even think that I will actually prove this theorem. It's always like that. We are, Okay, so what is the idea of the proof? You have these matrices and you look at these products, and what to do with these products you have. It is absolutely unclear. What turns out is the following thing, that you shouldn't actually look at the product of matrices and look at the norm. You should really look at the following thing. You see, you should look at A of n applied to x, and strangely enough, raised to this power minus alpha. And you should take an expectation of this. I am explaining the idea of the proof now. What I will in fact prove is the following thing, that there is an alpha which is positive, and such that the expectation of this number, of this sequence of random variables, and now actually there will be an integral over dsx here over the sphere, over the unit measure. What will happen is that this thing will, what should happen with it? If we believe that it will grow, that this guy is growing exponentially for a typical value of x, then this should decay exponentially. It's not exactly true, but for some values of alpha it is true. It will behave like e to the power minus delta n, where delta is strictly positive. If I know that, I am done, because I don't want to be let me see. Because what is the probability that the norm of A of n, will be larger than e to the power epsilon n, or smaller, sorry, smaller than e to the power epsilon n for every epsilon larger than 0. Every fixed, I fix an epsilon, fix epsilon larger than 0, but then if for every epsilon larger than 0, this thing happens with a large probability, am I right? Large or small? We shall see in a minute. Then, if this happens for every epsilon with probability which is close to 1, then clearly it is a non-growing, a sequence which is not growing exponentially, the norm of n. This is what it means to say that a sequence of numbers, norm over n, does not grow exponentially. This is exactly what is true, of course. But what I want is, in fact, to use the Chebyshev inequality and to prove that if I have this estimate, then this can happen with only with an exponentially small probability. Okay, let's see.
Well, the lower one is not a statement, so the probability of this is large. This is what can't happen.
Yeah, but what I will prove that the probability of this inequality is exponentially small. This is what I will in fact prove. That there is an epsilon which is positive, such that the probability of this inequality is exponentially small, and that means that for this epsilon, for infinitely many values of n, you will have the norm of n, well, for all but finitely many values of n, a of n will grow exponentially. And this is all what I need, because I already know that it behaves like e to the power gamma n. I know that. You know already from the Kingman's theorem that the norm of a of n is e to the power gamma n. I only don't know whether gamma is positive or not. So the only thing I have to establish is that with probability which is close to 1, or actually 1, asymptotically, this product grows exponentially with some exponent, whatever the exponent. Now, how do you prove this? Or how you try to prove this, rather? This probability, well, I'll put the equality sign here, and I will continue there, is the probability that the norm of a of n x, to the power minus alpha is, of course, I simply raise it to the power minus alpha, larger than e to the power minus alpha epsilon n. This, of course, I want to prove that this probability is very small. So it's less than the probability that the norm of a of n x will be larger, well, larger or equal, if you are very precise, minus alpha epsilon n. I have put in an x, and now my x is not a fixed vector, it is a random vector which is independent over n. This is by definition. which is independent of this matrix and has a uniform distribution on a sphere. And obviously, this I need in order to use this expectation and to say that this is less than or equal by the Chebyshev inequality. Sometimes it is called Markov inequality. Then, what the expectation of this, oh sorry, I forgot the minus alpha here, of this to the power alpha with respect to these two measures. And I have to divide by this huge factor. Okay. This will be less than or equal than e to the power alpha epsilon n, an exponential factor which is growing exponentially fast, expectation of the norm of a of n x to the power minus epsilon. If this grows like e to the power, if this decays like e to the power minus delta n,
You also have to integrate over x.
this expectation is supposed to be taken over x and over omega. Of course, it is not a very good way of writing it, but I think that writing it like this, putting a dot there, is even a worse way than this one. So it's not a very good, of course.
So all the analysts, of course, know the Chebyshev inequality, but not all of us are analysts. So are you going to assume that we know Chebyshev?
I will at least state it. It is a very elementary inequality, and I will at least state it. But at the moment, you believe me that this is what it is. I want to finish the logic here, to explaining the logic of this thing, and then I will go back and say what is the Chebyshev inequality. So this is e to the power minus delta n. This is smaller than that, so this is less than e to the power alpha epsilon n alpha epsilon, sorry. This is less than or equal than e to the power. I have alpha epsilon here minus delta times n. You see, delta is fixed, epsilon is of my choice. I can choose it so that this thing is negative. And then the thing decays exponentially, and if this decays exponentially, that means that this probability is exponentially smaller than tends to infinity. And this in turn means that this event, with probability 1 happens only finitely many times. You observe it only for finite values, for finitely many values of n. This is the so-called Borel-Cantelli lemma. So all what is left to prove is this thing. That this
upper one.
no
The upper one, you mean?
the upper one actually.
This one.
Yeah.
And Chebyshev.
And
Well, you don't have to
to
prove
prove the
it.
Chebyshev.
Just explain to the audience.
Of course, no, I would be happy, compared to what I have to do. It is just, a piece of cake. Such a trivial thing. Well, let me explain what is Chebyshev inequality. Indeed, it is not a good idea not to say it, at least. There is also the Borel-Cantelli lemma, which I used, and I can say also what is that. Now, if psi is a non-negative random variable, this is the form in which I use Chebyshev inequality. Expectation of psi is finite, then the probability that psi is greater than epsilon is less than or equal than epsilon is positive. there is a, okay, let's call it, okay, let me write it so that they are really different here. Expectation of psi divided by psi divided by epsilon. This is what is called the Markov inequality. It is a very simple inequality. I will still not go into the proof of it, but if you have a, yeah, it's a good exercise to do. And certainly, if you ever are going to prove anything that has to do something with probabilities, then you should definitely learn it if you don't know it yet. Now there is a much finer thing, and very often used by probabilists, much less by analysts, by the way, but still. And this is Borel-Cantelli lemma. If you have a sequence of events, let's say Bn be a sequence of events. Such that the probability, sum of the probabilities over n, Bn, is finite. Then, in this sequence, then the probability that you will observe infinitely many of them is 0. You see, what is a sequence of events? Event is a subset. If you have these subsets such that they, in a sense, decrease, then the number of elements here, which belong to infinitely many of them, cannot have a positive measure. I said a very simple thing. If they belong to infinitely many of them, then this cannot converge. This very set will lead to divergence of the series. So this is another standard tool in probability, a very useful one. I have just used it because my probabilities, the sum of these probabilities converge, and this is the reason why after a finite value of n, for almost every omega, I will not see this happening. It will happen only a finite number of times for almost every omega.
So can you write next to the statement Borel-Cantelli and shift that Markov?
Okay, yes, thanks. So, Markov or Chebyshev. Markov inequality. Borel. I'm not sure about the Cantelli. Something like that. I think it's correct. With C there? Oh, what an embarrassment. They never know how to write their own names. Okay. So this is a Borel-Cantelli lemma. In the simplest form, of course. There are, it's unbelievable what these guys do. They develop all these things. Anyway.
Okay, so now we still need to estimate the expectation of this.
So the whole thing is reduced to the question about the expectation of this thing, or this integral. And this is really a very in a sense an involved thing. You see, instead of looking, I will try obviously I will not finish the proof, but I will at least try to explain the idea. Ideologically, what happens, you trade in, you exchange, looking at the expectation of the product of matrices for looking at the expectation of a product of infinite dimensional operators, which is a horrible object unless you know that these operators, which we will construct in a second, have the property that they are unitary. I will consider the following operator. Vj of f of x, x belongs to S, and Vj f, G is a matrix, is f of G, x divided by the norm of Gx, a very simple thing so far. F is a function times 1 over the norm of Gx to the power, say, alpha m. Okay. Let me write it like this. M divided by p. I wanted to write it alpha m with alpha less than 1, but I will write it with m divided by p with p larger than 1. So p is any fixed number larger than 1. Say 1. You see, it is a linear operator on the space of functions. For every matrix G, I have a linear operator. But the remarkable fact, established first by Furstenberg, and at least this is to where I have the reference, is that this operator, I think people knew it, I cannot believe, but definitely used in a very useful way by Furstenberg and proved in his classical paper in 1963, is the following thing, that the norm of V J of f p in the LP space, I will write it, is the norm of f. In other words, this operator, this is a linear operator which preserves the norm of a function. It is not an obvious thing immediately, certainly not, but it is true. Let me try. What did I want to do? Okay. I wanted to say what is the norm of f. The norm of f, by definition, is the following integral of the absolute value of f of x ds of x over the sphere S to the power 1 over, oh, sorry, here there is a p, and here is 1 over p. It is not difficult to show that this is in many ways a remarkable identity. It is very easy to check the following property, that this is almost a representation. Yes?
You assume to be
G is a unity, is a matrix with determinant 1. This is essential. Otherwise, yeah, you can get anything there. G is a matrix with determinant 1. It is based on the fact, this thing is based on the fact that if you write here, if you write in this integral, if you put x equal to gy divided by the norm of gy, then g of x, 1 over g of x, the Jacobian of this transformation, you will map this sphere into itself. And instead of x, you will have gy divided by the norm of gy, but in order to have the integral, you will have to put in the Jacobian, which is equal to exactly 1 over the norm of gy to the power n. Since I raised the whole thing to the power, p I will have that this integral is equal to the integral of f. This is the idea. The other thing to note is the following, that v g1, g2 is equal to, you can easily check it directly, but also from what I said, it naturally follows that this is vg2 times vg1. They multiply into a product of operators So this is the first thing to note. The second thing is this. The third thing that you have to know is the following, that if I want the expectation of the thing I am interested in, of this, what I have to do, I have to apply, I have to consider the expectation of the operator of v n, v1, vn applied. I will be next time much more accurate. I now want to explain the idea. To the function 1. By this, I denote a function on a sphere which is a trivial function of at point x, and then I have to take the norm of this function.
Constant function.
Constant function, which is exactly 1 on an x. And I will have something like this thing here without the integration over x. I will have, again, here I consider the expectation with respect to the matrix on the omega.
And alpha will be m over p?
Something like that. I will say exactly. I want to finish the idea. Now, this is the expectation of the operators which are independent. You see, the point is that the operators now are independent, and the expectation of the operators can be simply written like this. This is v to the power n, 1, at point x, where v is the expectation of this operator vj, or say v1. Because
Question here. What is in the brackets on the left hand side?
so
That's his integral up there.
He didn't write again the long expression.
I didn't write the expression, which is the one we are interested in, this one. But this time without integrating over x. I said I will be much more precise next time. Now, you see, this operator is an integral. It is, you integrate over unitary operators, operators which preserve the norm. If you integrate operators which preserve the norm of this operator is likely to be less than 1. If it is less than 1, then, of course, this thing decays exponentially in a certain sense. In this space we were talking about. But this space will be exactly the one I need. And I will prove in this way that something is happening there, that this thing is decaying exponentially, exactly that. Because if the norm of the operator is less than 1, then this thing goes to, or tends to 0 exponentially fast. In this sense, it will be, we will see that this is exactly in the sense I need. This is how it works. And I will, of course, at some point use the fact that no measure is preserved by the group generated there, by the support. This, of course, has to be used, because otherwise it is simply not true. I think I have to stop.
The audience still has the final word on everything, yes?
I'm still a bit confused concerning the third equation there. So the left-hand side depends on alpha as far as I understand.
Yeah, but I will choose alpha in a proper way.
So we choose alpha, and after this we'll get something.
Of course, alpha will be something like 1 over p or something.
So at the beginning of the Monday lecture, you will fill in the details of this argument.
I hope so, yeah. All right. No, I certainly will. That's only that I think that I am really, when I prepare my lectures, I think I have nothing to say there. Everything is clear, and it shouldn't take more than half an hour to explain. Then at the end, I see that I haven't explained about a half of what I prepared, so instead of half an hour, it has to take
But at least
2 hours at least.
give some impression.
No, but I think that this is exactly what is more important, that you have the idea of what is happening there. You see, you have to look at some non-trivial things there. Yeah.
Any more questions? Comments?
So is this the way Furstenberg did the proof? Are you following?
It's very close to what Furstenberg did. Very close. In fact, this way was much more explicitly explained by Wurzer in his work in 1980, much later than the first proof has appeared. If you look at the first proof, no, essentially, as one says, but it looks very different. But essentially, and nobody has ever pretended that there is a single idea that Furstenberg didn't know at this point in Wurzer's paper. But he really presented it in a much more transparent way for a more general case, for products of Markov matrices, for the case of Markov dependence.
Does this proof also apply to, will this give you all the Lyapunov exponents positive? Zero, sorry.
No. Not immediately. No.
As far as I remember, the Furstenberg himself, he just said that it is a the maximum exponent is positive. Yes.
Yes. I'm talking at the moment. Everybody understands. I never said a word about other exponents.
So 2 by 2, of course, but 2 by 2.
I will.
2 by 2,
I
we
hope
need not all this stuff.
to be able to say a couple of words about other exponents. Definitely not prove anything serious about that. But it doesn't work.
Is it a variant or not? Can you obtain all exponents by a variant of this argument?
No, not really. Not really. No. You need new arguments. So in order to distinguish them, you really need some other ideas. It's not not at all immediate.
So let's have tea, and please be back at 4 o'clock. We're having 2 research seminars today.
2.
2.
There was an announcement about 1.
We're having 2, and that is